Okay, thanks a lot for the introduction and the invitation to the workshop. I'm looking forward to all the talks. As said, I work in Germany in KIT, but we're actually settled in a place called InnovationLab, which is centered about printed technology. What it means is that we combine a technology that has already existed for a couple of years for printing newspapers and packaging with functional links that could be semiconductors, oxides, etc., to produce optoelectronic applications, from light emitting devices to photodetectors and lately wearable electronics. As it was already discussed before, the idea of using printing is to contribute to sustainability by reducing the use of materials, reducing waste, as well as enabling low temperature processes. It has been pointed out in the introduction by David that there is so many applications on electronics that are actually pulled by the demands of the market, demands of the society. However, there are open questions about how much resources do you need, what is the energy efficiency of all these devices, and what would be their life cycle. So I think it's very important that all of us are together interested in how to bring some bio-friendly, eco-friendly, or biodegradable material concepts to try to address these open questions. From our side, our group has been working for a long time in light emitting devices, and we have concentrated in a device, an alternative to an OLED, which is called a light emitting electrochemical cell, that in principle is a sandwich between two electrodes. You sandwich an electrolyte and a semiconductor. You applied some voltage, these ions redistribute and help the electronic and physical processes inside the device to generate light emission. This works quite well, typically in a lower performance of OLEDs, but it's more easy to process because they only have one active layer in between. This is an example how we managed in the past to perform gravure printing to fabricate them, as well as inkjet printing, where we could have ultra flexible devices on the basis of polymeric materials. So our take on how to include some sustainability aspects or some biodegradability aspect in these materials was to concentrate on the solid polymer electrolyte, which is composed of a salt and a polymer that would help these the ionic movement. So these would have certain requirements that I will not go into detail at the moment. But we said, okay, what happens is that instead of taking what would be high performing and optimized for this, we take some synthetic polymers that are known to be biodegradable. So for example, by hydrolysis routes, like polylactic acid, polycaprolactone, and some copolymers from the same family of materials, and see if we could actually do them to have use them to have a functional device. To make the long story short, it actually works. This would be a device on the basis of an emitter called super yellow, which is a commercial material. And this ionic movement was enabled by an electrolyte formed by PLGA, this biodegradable polymer, and salt with a complicated name. The luminance we achieve, it's around 3,000, 4,000 candelas. Your screen of the TV or your phone has around 2,000 to 6,000 candelas per square meters. However, we had short lifetime. Our best working hours at the moment is this copolymer, in which we could basically have 3 times the performance in light emission, very low operation voltage, and a lifetime for around 100 hours. That could be very short for using it for a high demand, for demanding applications such as the display of your TV, but you could think on short lifetime applications like packaging or like lab on chip and so on, that you could probably have enough time within these 100 hours and have a material that could partially degrade. Obviously, we did these materials on glass and on glass substrates, something that was more standard and reproducible, but we also took a look into how you can deposit these kind of devices on biodegradable substrates. For this, we chose cellulose diacetate, which is already can be taken as a compostable material. It is transparent, which is important for optical applications. And it's also thermoformable, which help us really to planarize this surface and be able to develop a process like this one, in which we could generate these devices. So we had a combination between inkjet printing and coating techniques to fabricate this device that is semi-transparent and flexible and has light emission. Due to the processing and not optimized substrate for optoelectronic applications, we lost a lot of performance, but still we have around 200 candelas per square meter. The highlight of this work is that if you take into account the substrate of this device, we're almost 99% made of eco-friendly materials. We took a look to a different type of device, which is also driven by electrochemical processes, which is electrochromic devices. This is a device that changes color when you apply the voltage. You've seen it already in some planes. They have these electrochromic windows, so you'll see it coming for packaging and signaling. So what we came up with, one of my students came up with, was to fabricate it on the basis of at least either biodegradable, biosourced, or not cytotoxic material. So we have, again, cellulose diacetate as the substrate, gelatin as an electrolyte, PWPSS is a polymer that will change color with voltage, and it's proven to be cytotoxic, as well as gold, which is an inert material. So you can see here that is wearable, it can attach to skin, and when applying a voltage between an electrode and the electrolyte, it can change color. The advantage of doing this by inkjet printing is that we could change with the same process that with the vellum, we can, by digital design, we change the layout that we wanted to print, as well as the sizes and so on. So already with a single process, you would be able to do many applications. And our highlight would be that we actually approved, or we passed a standardized biodegradability test. What you see here is that our device degraded 70% in less than 24 weeks, which would be this validity criterion for this test, and it performs in biodegradability better than the reference. However, this success does come with a warning. I mean, it is very important, and I think it's a nice step to start demonstrating biodegradable devices that can be used for electronics. But one would need really to make an analysis if your whole process is energy efficient, if all the energy you put into fabricating all this device is actually in a positive balance after it's degraded. So perhaps, and something that we have not done in detail in our research, is to see which parts of it would be better to recover, like gold, or would be better just to leave in the ground for compost applications and so on. This has to do also with where the materials come from. Just to conclude, and just to give you let's say some sort of look into the future of what we're doing, we're taking a look at biosource materials. We're working on a DNA-based electrolyte. This DNA was processed from waste from the fish industry, and we managed to fabricate light-emitting devices with a variety of colors due to the good electrochemical properties of DNA. With this, I'll conclude my talk. I hope I showed you that we can fabricate eco-friendly optoelectronic devices, or at least going towards a more eco-friendly production of them. And I show you how some biosource and synthetic materials can enable these goals. And finally, last but not least, how functional digital printing can help to link these sustainable use of materials towards sustainable technology. And I want to thank all the team that actually does the work, collaborators that help us synthesize some of these materials, funding, and you for your attention. And it's time for questions if you have any. As an advertiser, I have 2 open positions for PhD students. If there are any master student interested, just send me an email. Thanks a lot.